All right. So yesterday, well, let me see. Oh, I guess it's doing that. All right. So yesterday we talked about the two necessary components for a circle. You need the center and you need the radius. So if we have those two pieces of information, we can write the equation in standard form. And if you recall the equation in standard form, so the equation of a circle in standard form is the x minus h quantity squared plus the y minus k quantity squared equals the radius squared. So if I have the center and the radius, or I have pieces of information that would allow me to find the center and the radius, I can write the equation. And that gives me the circumference. Like I can draw the circle from there. But what happens if I'm interested or I'm looking at problems that require me to look at all the points inside the circle? Or all the points outside of the circle, not just on the boundary of the circle. So instead of having an equality, we're going to have an inequality. So if we see a less than a certain radius, then I'm inside the circle. And if I see a greater than a radius squared, then I'm going to be outside the circle. So if I'm trying to answer a question, for example, think about when you order a pizza. Back in the day, maybe now with Uber Eats and all those other things, they'll just deliver it anywhere, right? But back in the day, when we used to order a pizza, they'd say, well, what's your address? And you'd have to give them your address. And then they would say, oh, no, you're too far away. We don't deliver that far. So how were they figuring out what, if you were close enough for them to deliver it to you? Well, they would actually have a little region, right, on the map, and they would say, do you fall in this region? So if it were a circular region around the restaurants, then they would just see, are you inside a certain distance away, within a certain circle radius of the restaurant? So let's think about this. If we have a restaurant located at -1, 1. So let's go to -1, 1. -1, 1. Here's my little restaurant. Okay. That's where I want to order food, from this little restaurant right here. And I want to know which homes are within a 4-mile radius, within 4 miles of the restaurant. So this is my HK. That's going to be the center of my circle. And then what does this within 4 miles represent? The radius. So my radius is going to be 4, but I want to look at everything that's less than or up to 4 miles, right? Within is going to be inside and on the boundary, right? So I can actually set up a circle, and I could draw the circle if I wanted to, but what would the equation of this corresponding circle be? It would be what? Mm-hmm.
Plus y minus 1 quantity squared is equal to 4 squared.
Okay, and I want to make sure that I'm within 4 miles, right? Now, that's radius squared, right? So that would be 16. So it would be x plus 1 quantity squared plus, let me just rewrite that because that's a little squished, right? So our radius is 4. So I'm going to go 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And so I know this is kind of the circle, but if I look at, oh my gosh, it's kind of hard to, I don't know. I mean, I know certain houses are within that 4-mile radius. So if I look at all the houses, let's see, what do I have? I have house A, I have house B, C, D, E, and F. Now, some of them I can look at and immediately say, oh, yeah, they're within the 4-mile radius. Which ones do I already know just by looking at it? B for sure. Mm-hmm. C for sure. D for sure. And it kind of looks like E is, but we really don't know. So how could I figure out if those houses are close enough within the 4-mile radius? Substitute what? The points, okay? So what's the ordered pair that corresponds to the location of A?
2, 4.
2, 4. Okay, and then B we said was good, C was good, D was good. We don't really have to check it. We could. What is the ordered pair that represents the location of house E?
1, -2.
Okay, 1, -2. And what about F?
-2, -3.
-2, -3. Okay, so I could take those and I could substitute in for the X and the Y value and see if it makes a true statement. So let's go ahead and do that. So I have, so that's going to imply that I have 2 plus 1 quantity squared plus, Y is 4 minus 1 quantity squared. And the question is that less than or equal to 16? Yes or no? No. So A gets no food from that restaurant. Okay, go ahead and check E and F. Does E get food?
Yes.
E gets food. Do you agree, Connor? That's a true statement. What about F?
No.
No food for F. Okay, so we can just create the circle, the radius with a certain radius, and we can look at all the houses that are within that radius. So in this case, the only ones that satisfy this inequality are A, B, C, D, and E. So of course, this is a word problem. We'd answer the question. The only homes that are within a 4-mile radius of the restaurant located at -1, 1 are houses B, C, D, and E. Okay, excellent. All right, so now let's think about how we're going to do the graphing on the calculator. So when we enter in equations, we said that circles are not functions, right? They don't satisfy the vertical line test. There are more than one y value. There's more than one y value for every x value. Now, if you think back to how we entered in equations so far into the calculator, we went to y equals, right? Well, but in this case, if I'm looking at the equations in standard form, like for example here, this is not y equals. So how on earth am I going to be able to put that equation into the calculator? I have to solve for y. So let's first think about what this graph should look like. So can you tell me what the center is? It is 0, 0, right? H and K are 0. X minus H, there is no H. Well, it's 0. And then what is the radius? 7. So, I mean, I could technically sketch this by hand, right? The center is at 0, 0. I go to 7 to the right, 7 up, 7 to the left, 7 down. And I know what my little circle should look like, right? But I want to be able to graph this on the calculator. So how would we go about solving for y? What would we have to do first?
Bring the x over.
That's right. How?
Subtract x squared.
Subtract x squared from each side. So that sums to 0, leaving me y squared equals 49 minus x squared. But I don't want to put y squared into the calculator. I need to put y into the calculator. So what would I do next?
Square root both sides.
Square root each side. That's correct. So now I'm going to get y equals what? I'm going to get plus or minus. So maybe let's go ahead and write that both ways. So I get 49 minus x squared as the radicand, but it's plus or minus. So how am I going to put this into the calculator? Well, I'm going to put into y1 49 minus x squared and y2 negative 49 minus x squared. So let's go ahead and put that into the calculator and see what that looks like. So we have 2 parts to build this circle in the calculator. And when you put these 2 equations into the calculator, do we get the graph that we sketched by hand? Remember, you may have to modify your window based on what you were last graphing. Do you get a graph that looks like a circle?
No.
No, not quite. What does it really look like? Which conic does it look like? We have 4 conics. Do we know what the 4 conics are?
Yes.
Okay, so
What was the oval one?
so we have a circle. What's the second one?
An ellipse.
A hyperbola, 2 branches, and a parabola. But when you put this into the calculator, it looks like what? An ellipse, right? So it's actually quite accurate. What it's graphing this piece. That's the first, that's y1, right? And then y2 is this lower semicircle. But what's happening is that the window that it's creating, the way it's looking at the axes, is it's not a square, right? So what you have to do, if you want it to actually look like a circle and not an ellipse, even though it is really a circle and not an ellipse, you're going to go to zoom 5, which is z square. So that will allow it to actually graph it where it looks like what it really is. So now if you go to zoom to 5, z square doesn't look like a circle. Yes, it does. Okay, so don't just look at the graph without thinking about it, right? We know this should be a circle. We have the upper semicircle, and we have the reflection across the x-axis, which is the lower semicircle. But for us to actually see what it looks like as a circle, we need to do the zoom 5, the zoom square. All right, now they get a little bit more interesting. So what if I have this equation? Again, bless you. I know it's a circle because I have x minus h quantity squared plus y minus k quantity squared equals r squared. So again, I can easily identify the center and the radius. What would the center be?
1, 1.
1, 1. And the radius? 1. Is 1. Okay, so again, I could graph this by hand, bless you. I could go to 1, 1. There's my center. I like a little C for my center. And then how do I graph the circumference?
Just 1 away from
1 to the right, 1 up, 1 to the left, 1 down. So kind of like we did yesterday, where we went ahead and talked about the domain and the range. But that's what the graph should look like. But remember, to be able to put it into the calculator, we have to solve for y. So what would be the first step? I'm isolating the y.
Okay, so you bring the x to the other side. Are you subtracting?
I have to move this whole term to the other side. Yes, I have to subtract that entire quantity from each side. So that sums to 0. Leaving me y minus 1 quantity squared equals 1 minus x minus 1 quantity squared. Now what would I do?
Square both sides. Square root both sides.
Square root each side. So I'm going to square root this side, and I'm going to square root that side. And when I do, I get plus or minus the square root of 1 minus x minus 1 quantity squared. No, I don't. There's no squared here. Now what? I still want to isolate the y. What would be the next step?
Adding 1 to both sides.
Add 1 to each side. So I really don't even need those parentheses, right? So now I can add 1 to each side. But we have to be careful how we're adding 1 to the right-hand side, right? Because this expression inside the radicand is inside the radicand. So when I add 1, I'm not adding it to anything inside the radicand, inside the square root expression. So I could even rewrite this, if it makes us more comfortable. 1 plus or minus the square root of 1 minus x minus 1 quantity squared. Now, I have 2 equations I can put into the calculator now, don't I? I have as y1, 1 plus the square root of 1 minus x minus 1 quantity squared. And for my y2, I have 1 minus 1 minus x minus 1 quantity squared. So go ahead and put that into the calculator. And we have to be very careful that for that radical expression, we put parentheses around the entire radicand. And see if you get this circle, which we know what it should look like. So we have to be very careful with our radical expressions.
Why do we have to put parentheses around the radicand?
Well, because if we're not careful, right, the calculator, I always err on the side of making sure that it knows what's inside the square root, right? So it does the square root and it opens the parentheses, right? So you just make sure you need to close the parentheses. If we had rewritten this where this was first and this was second, we want to make sure that we're closing the parentheses so we know that plus or minus one, that this one is not inside the radicand.
Okay.
So that's kind of why I rewrote it to begin with, to like not have that issue.
Okay.
Are we good? We got the cute little circle where it's supposed to be, and it looks like a circle. We got our circle? We got our circle. Oh, a cute little circle. All right, now we talked about the degenerate cases. So when we were slicing that cone, the double-naped cone, we know how the angle at which we were slicing the cone to get each of the conic sections. But to get the degenerate conic section, where did we have to slice the cone? What restriction did we have? The vertex, right? We had to slice through the vertex. So if we think back, what was the degenerate for a circle, the degenerate conic?
A point?
It was a point, right? What was the degenerate for an ellipse? The degenerate case. It was also a point. What was the degenerate case for a parabola? A line, and the degenerate case for a hyperbola. Two intersecting lines, right? So if I think about the degenerate cases, we need to make sure we understand what's happening. So what I want to look at is I want to look at the instance that I have this standard form of a circle, but notice what's on the right-hand side. On the right-hand side, it's saying that r squared, r, is 0. Right? So the radius is 0. So if there is no radius, I am just at a point, right? I'm just at the center. Does that make sense? So we know that the degenerate case of a circle, in this case, the equation standard form of a circle, where the radius is 0, is just a single point hk. But what happens if the radius is negative? Can you have a negative radius? No, because the radius represents a distance, right? So if you actually work out a problem where you're getting an equation maybe from general form into standard form, and you end up getting a radius that is negative, that's not possible, because the radius represents a distance. So there is no graph of such an equation on the Cartesian plane. Now, let's play a little bit more. And let's look at tangent lines to circles. So let's think about what a tangent line is. So if we think back to geometry, a tangent or a tangent line is a line that exists in the same plane, on the same Cartesian plane, on that same little whiteboard or surface or piece of paper. And this is a line that intersects the circle. So here is our line that is intersecting the circle at one point. So that's the point of tangency. That is the point on the circle where the line touches the circumference of the circle. So if we think back to geometry and we think about the relationship of this tangent line to the circle, we should notice that, okay, here's my center of my circle. And if I draw a radius to the circumference of the circle where that line is tangent, do we know what degree measure is the angle connecting the radius to the tangent line? What is this angle here? It's 90 degrees, so it's perpendicular. So if we think about tangent lines to circle, those tangent lines are perpendicular to the radius of the circle. So let's look at this example. It says write the equation of the line. So we're writing the equation of a tangent line given this circle whose center is what?
24, or 0, 0.
0, 0. So we're at the origin. And then if we look at where this tangent line, or where this line is tangent to the circumference of the circle, it's at the point 3, 4. So if I'm trying to write the equation of the line, right? So I'm trying to write the equation of that line. What might I need to do first? Before I can even get to the tangent line, there's another line segment in this circle that I do know. The radius, right? So the first thing you want to do is you want to find the slope of the radius, that little line segment. So how am I going to find the slope?
Take the 2 points.
Use the 2 points that we know, and we have the slope formula. Now you may be saying, well, why can't I just count the rise over the run? Well, you can, but what if they're not integer values? What if it's very hard to tell those points? So I'm going to use the slope formula, right? And I'm going to have y2 minus y1, change of y over the change of x. Again, it doesn't matter which one you're calling point 1 and which one you're calling point 2, but you do have to keep track of that. So let's go ahead and call this point 2 and this point 1. And let's substitute into the slope formula. So what do I get? What's y2?
4.
4 minus y1
0.
over x2
3.
minus x1.
0.
So the slope of the radius, so I'm going to put a little subscript r for radius, just so I know that I'm looking at the slope of my radius. The slope of my radius is 4/3. So the slope of the radius is 4/3. But I don't want the slope of the radius. I want the slope of the tangent line. So what is the relationship between the slope of a line and the slope of a line that is tangent to it, meeting at 90-degree angles? So I'm going to say the slope of the tangent line. If I know the slope of the radius, what is the slope of the tangent line?
So like negative reciprocal.
The negative reciprocal. That is absolutely correct. So while the slope of the radius is 4/3, the slope of the tangent line is what?
Negative 3/4.
-3/4. Connor, do you see that? Okay. So I now have the slope of the tangent line. I want to write the equation of the tangent line. So now, so this is the slope of the tangent line, or the line that is tangent to the radius. So the slope of the radius, or the line segment that is the radius, and the slope of the tangent line. So now I can start writing the equation. So I can either use the point slope form or the slope intercept form. I don't care, but since we've already kind of been working with the slope formula, we might as well use that. So we have y minus y1 equals the slope of the tangent line, because that's what we're writing the equation of the line of, x minus x1. So I'm going to use the point slope formula to write the equation of the tangent line. So I'm going to use y1. So I'm going to use 0.2, because I don't want to use 0, 0. So I'm going to have y minus 4 equals the slope of the tangent line, which you said was negative 3/4, times x minus 3. Do we see why we're using the 0.34 instead of 0, 0? Why?
Because that's just y equals.
Yeah, but why am I choosing to use this point instead of 0, 0? Connor, do you know? Why are we using 3, 4 to write the equation on the line and not 0, 0?
Because 0, 0 isn't on the line.
0, 0 isn't on the line, right? We're writing the equation of the tangent line. Okay, so now if I wanted to put this, I mean, this is an equation. That's in point slope, slope using the point slope formula. But if I want it in slope intercept form, I have to do a little work. What would I have to do?
Isolate y.
Isolate y. Okay, and then what else?
Distribute -3/4.
That is correct. So I'm going to go ahead and do this. Move the y to the other side by adding. And then you are correct. I do need to distribute. And then I need to actually combine like terms. So I have to get a common denominator. And what is the equation of my tangent line?
-3/4 x plus 25/4.
That is correct. Y equals, because it's in a line, right? Y equals -3/4 x plus 25/4. Did we get that? Okay, good. All right, let's try another one. Write the equation of the line that is tangent to this circle at this point. Now, you can draw it. If you like to see things, you can draw it. So what is the center of that circle?
1, -2.
The center is 1, -2, and the radius is
5.
5. So 1, -2 is my center, and my radius is 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I know this is my circle. And I know that I have a line that is tangent at the point 5. 1, 2, 3, 4, 5. -5. 1, 2, 3, 4, 5. Something like that. So it looks something like that. So if you like to sketch what you've been given, sometimes that helps. Especially if we want to look at this, we know that the slope is positive or negative? Positive. So at the end of the problem, if we get an equation that has a negative slope, we've done something wrong. So I personally, on quizzes and tests, you'll get graphs just to help you, even if you're asked, not asked to graph it. Okay, so what do I have to do first? What did we do in the last one? If I want to write the equation of the tangent line, we first had to look at what?
The radius.
The radius. So I need to see this. I know this point was given. This point was 5, -5. And I know the center was 1, -2. So if I look at the slope of the radius, what is the slope of the radius? We're substituting in the center and the point where the line is tangent, and what did we get?
-3/4.
That is correct. -3/4 is the slope of your radius. And so if I want to know what the slope of the line that is tangent to it, what would it be?
4/3.
It is 4/3. And I could also write the slope that is perpendicular. So I could write a little subscript of t, or I could even show that, I'm looking at the slope of the line that is perpendicular. Either one of those to help you keep track is fine. Now, I have the slope of the tangent line. I now need to write the equation of the tangent line. So I'm going to use the slope of the tangent line and the point on the tangent line. So let's go ahead and substitute into point slope formula the information that we know. We have the point, we have the slope, and we solve for y, and what do we get as the equation of the tangent line?
4/3 x minus 35/3.
Equals y. That is correct. Did we get that tangent line? That's lovely. That's lovely. So we do want to start thinking about that, because you are going to be looking at this tangent line is going to prove to be very important in your math career. So if you think about when we looked at the difference quotient, we were looking at the slope of the secant line passing through a nonlinear function. When you get to calculus, you're going to really care about that tangent line. That point where it's touching a curve, it won't be a circle necessarily, it's going to be another curve, and you're going to care you're going to care about that point. That tangent line is going to prove to be very important. It's going to tell you a lot about that curve that you're working with. So you have a lot of practice in here on circles, a lot of practice on circles. You should be able to do all of these practice problems. You now can do these because that's what we did today. And then we will start with the ellipse in the next class.